So good day, netizens. So today we'll be talking about our ideal solutions prepared by yours truly. But first, let's go into what solutions are. Solutions are homogeneous phases composed of different chemical substances. So instead of just one chemical substance, there's usually two or more. For a component I in a solution, we can define the mole fraction xi as the number of moles of component I over the total number of moles of the system. So why do we study solutions? We study solutions because most of our materials or substances are actually impure. Previous calculations in our previous modules, free energy and equilibrium, we assume that we have pure substances every time or something like that. But most substances usually are impure. And the impurities incorporated in our materials or in our substances are actually enough, even if sobrang liit lang, even ppm amounts, can drastically change the physical and chemical properties of substances. So an example of this is for your semiconductors. In the doping of semiconductors, we add trace amounts of dopants. So it can be phosphorus, nitrogen, arsenic, gallium into our silicon. So we usually replace one silicon atom out of a million silicon atoms and replace it with an impurity atom like arsenic, gallium, nitrogen, or phosphorus. But when we look at the electrical conductivity of these substances, replacing just one piece of silicon with a impurity atom actually increases the conductivity of the said crystal by around 100,000 times at least. So clearly there is a need to consider the effect of these impurities in our materials. And in the same vein, there is a need to consider the effect of these impurities in our delta G calculations. So now let's define what a solute and a solvent is. So in a binary system, your components may be classified as solvent and solute. So binary system is just a system with two components. So a solvent, this is the component present in the greatest amount, is much more than our solute, or we also name this as our host atoms. So for example, in salt water, our solvent is water. Meanwhile, for a solute, this is the component present in a minor concentration. So this is the trace amounts usually in our materials. So salt water again, it's the salt now. So usually, going further in this module, we'll usually consider the situation in which we have dilute solutes or dilute solutions. So when we talk about dilute solutions, basically the concentration of the solute or the number of solute atoms is usually much less than our solvent atoms. So other examples of solution, we have the atmospheric air. So that's composed of nitrogen, oxygen, and other gases. We also have our different alloys like brass, bronze, gold alloys is also a solid solution, and so on. And we have the common like water-based solutions. So now let's go to our ideal solutions. An ideal solution is a solution in which we follow Raoult's law. So due to Raoult's law, what we'll find is that for ideal solutions, the activity of the component I will be equal to its mole fraction xi, the mole fraction of I, for all temperatures and pressures. So that is for ideal solutions. So we say that a substance exhibits ideality for a certain parameter, so for example, there's certain temperature and pressure when the activity of the component is equal to its mole fraction for that specific condition. So ideal solutions are formed because the mixtures between, the bond energies between unlike components A and B is the average of bond energies between the interatomic attraction of, let's say, A with A and B with B. So there's not much difference between the bond energies, and there we have no positive or negative deviation with respect to that one. So it's like we're just taking like the average of the bond energies, and in the balance, there's not really any deviation from ideality. Anyway, So now that we have some idea on our ideal solutions, let's try to solve a simple problem in extractive metallurgy about our ideal solutions. So example 2, in our module 6, the residual zinc and lead containing no other impurity can be removed by passing chlorine gas at 390 degrees Celsius or 663 Kelvin according to the following reaction. Zinc in our mat plus lead chloride in our slag would form lead in our mat and zinc chloride in our slag. So just a bit of clarification here. Definition of terms. You have your mat and your slag and your mat. This is your slag and yung nasa taas natin. Baliktad. This is your slag sa taas and yung nasa baba. This is your mat. So in extractive metallurgy, basically the slag and the mat are just two immiscible. So pag immiscible tayo, let's go with black. Immiscible. They are immiscible solutions. Hindi sila naghahalo. Kinda like oil and water. So sa slag natin, usually ang nakita natin dyan is our waste products. Meanwhile sa mat naman, this is where our refined product goes. So in this case, you will see from the reaction, we are actually refining lead. We're refining lead from lead chloride 2. And we're taking off the zinc in that situation. So what will happen here is your mat would contain lead and zinc, since we're extracting for lead. Meanwhile, slag natin, we have a combination of PbCl2 and ZnCl2, or our waste products, undesirables. Ito yung mga ating aliping sa gigilid. So from the problem, the standard free energy change of the above reaction, this one at 390 degrees Celsius, negative 63,137 joules per mole. And the final chloride slag has a mole fraction of zinc chloride 2, X of ZnCl2 equal to 0.983. The activity of zinc and lead at the above temperature for a very dilute solution of zinc and lead is given as the activity of zinc is equal to 29 times X of zinc, or the mole fraction of zinc. So we are to calculate the level to which the removal of zinc can be carried out in this reaction in weight percent if the system PbCl2, zinc chloride 2, or the chloride slag behaves ideally. Atomic weights of lead and zinc are 207.2 and 65.38 respectively. So from these given, first let's set up our solution. We know that for any situation, delta G naught is equal to negative RT ln KEQ. Batas yan. Yung KEQ natin, we can express that in terms of activities of our products and our reactants. Here, we have activity of lead times the activity of ZnCl2 over the activity of zinc times the activity of PbCl2. They are in slag and a mat respectively. Different solutions sila. So different na treat nyo siya specially. So first, let's look at the activity of zinc. Activity of zinc is equal to 29 times X of zinc, or the mole fraction of zinc, in the mat solution. So important na i-note. So mangyari dito, your KEQ. Lagyan natin siya dito. Your KEQ here would be equal to, sa baba, 29 times X of zinc. Then, may sinabi rin siya, XZnCl2 is equal to 0.983. This is mole fraction. For a solution, the total of the mole fractions should be equal to 1. Total of the mole fractions should be equal to 1. In this case, this is the slag solution. In the slag solution, there are only two components, lead chloride 2 and zinc chloride 2. If lead chloride or zinc chloride 2, zinc chloride has a mole fraction of 0.983, then we can get that the mole fraction of lead chloride will just be equal to the remaining components, which is equal to 1 minus 0.983, or equal to 0.017. So dito sa baba, lead chloride mo, 0.017 siya. Sorry. And yung sa taas mo, this is 0.983. Since recall, sinabi rin ng problem that PbCl2 and ZnCl2 behaves ideally. So in this case, activity is equal to the mole fraction, which is ito and ito for zinc chloride and lead chloride respectively. And yung activity ng lead, this one, activity of lead. Yung activity of lead natin, we can get from something said in the problem. We have a very dilute solution of zinc in lead. So this implies that zinc is much less than lead. If that is the case, then your lead can be taken as if it is approaching an x. The x of lead is approaching 1. Or we can treat lead as if it is a condensed phase. And if that is the case, if lead is a condensed phase, we can treat the activity of lead as if it is equal to 1. We can approximate that one. Activity of lead is equal to 1. Going back to our delta G equation, delta G naught is equal to negative 63,137 joules per mole. It's equal to negative R, negative 8.314 joules per mole Kelvin. Temperature is 663 Kelvin. And we have itong different values natin. Ln of 0.983 over 29 xZn and 0.017. So in the problem, again, we're looking for the level of removal of zinc can be carried out in our solution. So we're essentially looking for the amount of zinc left in our solution, which we can get from x of Zn. Solving this equation for x of Zn, xZn is equal to 2.115 times 10 to the negative 5. So I'll spare you the how this was done. Basically, ginawa ko yan using Wolfram Alpha because my calculator has been not returned for about a year. Whoever you are, please return my calcu. Anyways, so ito yung mole fraction of zinc in our math after defining process. But since we are looking for weight percent, we are looking for weight percent. So ano yung weight percent of zinc? We can convert it from x of zinc. The weight percent of zinc will be just equal to the weight of zinc over the weight total of all the things in our math. Sa math lang. Kasi titingnan lang natin is itong solution na to. Yung math solution. Kasi ito lang may lead and zinc. Nandito lang si zinc. So in that case, we have mole fraction of zinc multiplied by the molecular weight of zinc times the mole fraction of zinc, molecular weight of zinc, plus molecular weight, mole fraction of lead, molecular weight of lead, kasi kailangan natin yung lahat ng components natin, total mass na. Putting in our values, x of zinc is 2.115 times 10 to the negative 5 times the molecular weight, 65.38 over, again this one, 2.115 times 10 to the negative 5, 65.38 plus x of lead, which is equal to 1 minus 2.115 times 10 to the negative 5 times molecular weight of lead, which is 207.2. Solving for this one, the weight percent will be equal to weight percent of zinc equal to, for emphasis, let's use my favorite color, yellow. Pero baka hindi nyo siya makita, so let's go for my second favorite color, or an off shade of my favorite color, which is this one, 6.67 times 10 to the negative 4. So this is the weight percent of zinc na kaya natin ma-achieve, or the zinc content of lead can be lowered to 6.67 times 10 to the negative 4 weight percent. So hopefully na-understand niyo yung solution for this sample problem. And I'll see you on the next time. Hopefully you all have a wonderful day today and keep on fighting on. Konti na lang. Let's go. Fight. Thank you.